Alright, in this lesson we look at continuity, and there's a definition of continuity at a point towards the beginning of this lesson, at interior points and at endpoints. And we're going to first start with example 1 here, looking at if the graph is continuous at these various points. So first, is the graph continuous at x equals 3? So right here at x equals 3. In order for it to be continuous there, that's an interior point. So the limit as x approaches c has to be the same as the value of the function there. And if you look at that particular spot on the graph where x is 3, okay, this point right here indicates the value of the function. Now, does the graph approach that point from both sides? It does. So yes, the graph is continuous at x equals 3, or negative 3. Okay, how about at x equals negative 5? Well, here's the value of the function. Now this is at a left endpoint, so we only need the limit approaching from the right to be the same. But you see that the function approaches a different value on the graph as x is getting closer to negative 5. So the function is not continuous there. Okay, how about at x equals 3? Does the limit equal the function value? It's approaching the same value from both sides, same value that the function has. So yes, it is continuous there. At 5, there's the function value. Now this is a right endpoint, so we're only worried about the limit coming from the left. Does the function approach the same value as the function value there? And the answer to that is yes. All right. And question E here, at what other values is the graph not continuous? Well, there are two other values other than the one we already identified at x equals negative 5. There are two other values where this graph is not continuous. And those two values are at x equals negative 2. Why is the function not continuous at x equals negative 2? Well, first of all, it's not continuous at x equals negative 2 because the function doesn't have an actual value there. In order for a function to be continuous, there has to be a value to the function there, and it has to be the same as the limit. So we have a limit that exists, but there is no function value there, so it's not continuous at x equals negative 2. The other place is at x equals 1. It's not continuous there because the limit doesn't exist. The limit from the left is 3, and the limit from the right is negative 1. And so since the limit doesn't exist there, the function is not continuous there. So those are the two answers to that. Alright. Then we actually look at the test for continuity here. A function is continuous if and only if all three of these are true. The function has to exist, function value has to exist there, the limit has to exist there, and they have to be equal. So let's look at example 2. Is this function continuous at x equals 2? Well, in order for it to be continuous, the function value has to exist at x equals 2. And it does. We're told here that the function value is 2 at x equals 2. So we've met the first part of our test for continuity. Next, does the limit as x approaches c of the function exist? And how we're going to tell that with this piecewise function is we're going to find the limit based on everything that's around that isolated function point that we know. And so if the limit exists, since this is the function everywhere where x isn't 2, that would have to approach the same value, or that would have to approach some value as x approaches 2. So we go ahead and we find the limit as x approaches 2 of this function. Now, I think I'm going to do this algebraically. If I try to handle this algebraically via substitution, this is a 0 over 0. So I'm going to go ahead and factor and cancel, and this is the same as the limit as x approaches 2 of x plus 6 times x minus 2, x plus 2 times x minus 2, And so it's the same as the limit as x approaches 2 of x plus 6 over x plus 2. That's 8 over 4. That's 2. So the limit does exist there. And the third test is the function value the same as the limit? The function value there is 2. The limit is 2. So they are equal to one another. So is the following function continuous? Yes. Yes, it is. All right. We're going to stop here for this video and continue with additional examples in the next one. All right. See you next time.